The question of whether we can predict the next El Niño or La Niña is no longer confined to the realm of academic curiosity. For millions of Americans, the ability to forecast these events means the difference between stable food prices and costly grocery bills, between manageable storm seasons and catastrophic hurricanes, between economic stability and billions in damages. El Niño and La Niña, the two opposing phases of the El Niño Southern Oscillation, ENSO, are among the most powerful climate drivers on Earth. They arise from shifts in ocean temperatures and atmospheric circulation in the tropical Pacific, yet their fingerprints extend across the globe, influencing rainfall in California, drought in the Midwest, hurricane intensity in the Atlantic, and even energy demand during winter. The challenge for scientists has always been turning this chaotic system into something predictable. In recent decades, agencies like NOAA in the United States and ECMWF in Europe have led the way, building sophisticated models to forecast ENSO months in advance. Their successes and failures highlight both the complexity of the climate system and the extraordinary progress humanity has made in anticipating one of Earth's most influential cycles. At the heart of ENSO forecasting are climate models, mathematical representations of the Earth's oceans and atmosphere. NOAA, the National Oceanic and Atmospheric Administration, has been at the forefront of developing these tools, relying on a global network of satellites, ocean buoys, and weather stations. Their Climate Forecast System, CFS, is one of the most widely used models, simulating interactions between ocean currents, atmospheric winds, and heat exchanges. Each day, NOAA's supercomputers crunch millions of data points to update ENSO outlooks, projecting probabilities for El Niño, La Niña, or neutral conditions up to 9 months ahead. Similarly, the ECMWF, European Centre for Medium-Range Weather Forecasts, runs one of the most respected climate models in the world. Based in Reading, England, the ECMWF model has consistently been ranked among the best in capturing large-scale ocean-atmosphere dynamics. It is widely relied upon by meteorologists, researchers, and even private companies who depend on accurate climate forecasts. By comparing NOAA and ECMWF model runs, scientists gain a consensus picture of ENSO's likely trajectory, blending their strengths to reduce uncertainty. Yet the story of ENSO forecasting is not simply one of triumph. Failures have been as instructive as successes. The infamous El Niño that wasn't in 2014 remains a case study in the limits of prediction. In early 2014, nearly every major climate model indicated a powerful El Niño was developing. Warm water pools in the western Pacific began to surge eastward, and scientists confidently issued warnings of significant global impacts. Farmers, governments, and industries braced for floods, droughts, and storms. But the expected El Niño fizzled. The warming never reached the thresholds required to sustain the event, and the world was left with a weak, short-lived pattern instead of the super El Niño predicted. Critics called it a forecast failure, but researchers learned valuable lessons about the role of subsurface ocean dynamics and the unpredictability of wind bursts in triggering El Niño. By contrast, the 1997-98 El Niño stands out as one of forecasting's greatest successes. Months before the event peaked, models predicted its intensity and timing with remarkable accuracy. Governments had time to prepare for heavy rains, flooding, and drought. The result was saved lives and reduced damages compared to what might have occurred without warning. The 2015-16 El Niño, another record-setting event, was also well predicted by models, demonstrating how far forecasting skill had advanced. Still, there remain grey areas. La Niña events, for example, are often trickier to predict. They can arise quickly and last longer than expected, as seen in the prolonged La Niña from 2020 to 2023. Forecast models correctly identified its onset, but consistently underestimated its persistence, a reminder that ENSO remains partly beyond our control to foresee. One of the most exciting developments in ENSO forecasting has been the rise of artificial intelligence and advanced supercomputing. Traditional climate models are computationally intensive, requiring days of processing on some of the fastest machines in the world. But AI approaches are beginning to change the game. Researchers are training machine learning algorithms on decades of ocean and atmospheric data, teaching them to recognize subtle patterns that precede ENSO events. These AI systems can sometimes outperform traditional models in short-term forecasting, spotting signals that humans might overlook. For example, experimental AI models have shown promise in predicting El Niño conditions more than a year in advance, beyond the spring predictability barrier that has long frustrated scientists. This barrier refers to the difficulty of making accurate ENSO forecasts when crossing the Northern Hemisphere spring, a time when the Pacific system is in transition. Supercomputers are also playing a critical role in refining hurricane forecasts, which are heavily influenced by ENSO. NOAA's new generation of high-resolution hurricane models, running on powerful computing clusters, now simulate storm structure, track, and intensity with greater precision than ever before. During La Niña years, when the Atlantic tends to produce more hurricanes, these tools save lives by narrowing evacuation zones and improving preparedness. The integration of AI into operational forecasting is still in its infancy, but the potential is enormous. Imagine a system that continuously ingests data from satellites, ocean buoys, and weather stations, updating ENSO probabilities in real time. Such a system could alert farmers in Iowa to plant drought-resistant corn months earlier, or signal ranchers in Texas to adjust their herd sizes before feed prices soar. It could warn coastal cities that an active hurricane season is likely, giving insurers and governments time to prepare resources. The combination of supercomputers and AI is transforming climate prediction from a reactive process into a proactive one, with the power to reshape how societies deal with risk. For Americans, the implications of improved ENSO forecasting over the next decade are profound. Agriculture stands to benefit most immediately. The United States is a global leader in corn, soybeans, and wheat production, all of which are sensitive to ENSO swings. More accurate forecasts will allow farmers to choose seed varieties, adjust planting dates, and make irrigation plans that minimize losses. Crop insurance programs could become more precise, reducing costs for taxpayers while protecting farmers' livelihoods. Energy markets, too, will feel the impact. If forecasts indicate a strong La Niña winter, utilities can prepare for higher natural gas demand in the north and invest in storage months in advance. If El Niño is predicted, energy providers can anticipate milder winters and stormier conditions in the south, adjusting their strategies accordingly. These preparations reduce volatility in energy prices, benefiting both businesses and households. Public health is another area where better ENSO forecasts will matter. As discussed in earlier studies, ENSO cycles affect flu season severity, mosquito-borne diseases, and heat waves. With more reliable predictions, public health agencies can target vaccination campaigns more efficiently, allocate mosquito control resources in advance, and open cooling centers before extreme heat arrives. Hospitals will have time to staff up or expand capacity, reducing strain during peak events. For communities vulnerable to flooding or hurricanes, ENSO forecasts combined with hurricane modeling could save lives by improving evacuation planning and disaster response. The insurance industry has perhaps the most direct financial interest in ENSO forecasting. Each year, insurers calculate premiums and set reserves based on expected hurricane and wildfire risks. La Niña years often bring costly hurricane losses in the Atlantic, while El Niño years may shift risks toward floods and wildfires. More accurate forecasts mean insurers can price policies more fairly and remain solvent even in catastrophic years. This stability trickles down to homeowners and renters who may otherwise face skyrocketing premiums or cancelled coverage. But perhaps the greatest benefit of improved ENSO forecasting will be psychological. Americans live with a growing sense of uncertainty as climate disasters multiply. Farmers wonder whether their crops will survive, coastal residents fear each hurricane season, and families worry about rising grocery bills. Reliable forecasts will not eliminate these risks, but they can reduce uncertainty. Knowing months in advance what type of season to expect allows families and businesses to plan, adapt, and feel some measure of control over forces that might otherwise seem overwhelming. Looking ahead, the next decade will almost certainly bring a mix of successes and setbacks in ENSO forecasting. Supercomputers will grow more powerful, AI systems will become more sophisticated, and satellite networks will expand, delivering unprecedented streams of data. NOAA and ECMWF will continue to refine their models, competing and collaborating in ways that push accuracy further. Still, there will be surprises. ENSO is a chaotic system, and no forecast will ever be perfect. Yet the trajectory is clear. Americans will have more foresight than ever before about how the Pacific Ocean is shaping their weather, economy, and safety. The broader challenge will be ensuring that this knowledge translates into action. Forecasts are only useful if they are heeded. Farmers must adjust planting strategies, utilities must manage energy reserves, governments must invest in resilient infrastructure, and families must take evacuation warnings seriously. The science of ENSO forecasting is advancing rapidly, but the societal response often lags behind. Bridging this gap will be the defining task of the next decade. In the end, the question, can we predict the next El Niño or La Niña, is about more than scientific accuracy. It is about the kind of future we build. ENSO will continue to shape the United States, whether we are prepared or not. With better models, smarter use of AI, and stronger public engagement, prediction can become prevention. It can mean fewer lives lost, fewer billions spent on disaster recovery, and a more resilient society in the face of climate's greatest cycle. The Pacific Ocean will keep sloshing between warm and cool phases, as it has for millennia. But for the first time in history, humanity has the tools to see those shifts coming, and the opportunity to shape our response before the waves of consequence crash ashore. The mechanics of predicting El Niño and La Niña are rooted in a delicate dance between the ocean and the atmosphere, and the progress made over the past 3 decades has been remarkable. To forecast ENSO, scientists must measure and simulate processes happening across an entire ocean basin. How trade winds strengthen or weaken, how warm water pools migrate east or west, and how heat stored deep below the surface rises to the top. NOAA's Climate Prediction Center runs one of the most widely cited forecasting systems, the Climate Forecast System, CFSV2, which integrates data from satellites, buoys, and ships into a coupled model of the ocean and atmosphere. This system, updated daily, produces ensemble forecasts, dozens of runs with slightly different starting conditions that show a range of possible outcomes. The ECMWF, on the other hand, runs its Integrated Forecast System, IFS, which is known globally for its high accuracy in medium-range forecasts and increasingly respected in seasonal climate prediction. These models are not just black boxes. They represent decades of research into fluid dynamics, thermodynamics, and statistical methods, encoded in billions of equations that supercomputers solve every day. Despite these advances, forecasting El Niño and La Niña is fraught with challenges. One of the most notorious obstacles is the so-called spring predictability barrier. This refers to the fact that ENSO forecasts made in the first half of the year, particularly between February and May, are far less reliable than those made later. The reason is that during this transitional period, the Pacific's coupled ocean-atmosphere system is naturally more chaotic, and small errors in initial conditions balloon into large uncertainties. Scientists can sometimes see warm subsurface waters moving eastward, a classic precursor of El Niño. But whether those waters will surface and sustain themselves into a full event remains hard to pin down. Conversely, trade winds might strengthen, hinting at La Niña. But whether the cooling will persist or fizzle out often depends on unpredictable bursts of wind or atmospheric noise. These barriers mean that, even with the best models, long lead ENSO forecasts carry a degree of uncertainty that governments and markets must account for. Failures in past forecasts highlight these limitations. The 2014 Phantom El Niño is still discussed in climate science circles. Early in the year, almost every model predicted a strong El Niño forming. The Pacific was warming and subsurface Kelvin waves appeared ready to surface. By summer, forecasters were nearly unanimous in calling for a powerful event. But then the atmosphere failed to cooperate. The trade winds never weakened enough to lock in the warming, and by the fall, what had looked like a sure bet collapsed into a weak, short-lived El Niño. Farmers, governments, and global markets had already braced for disruptions that never fully materialized. This misstep was humbling, showing that models, however advanced, cannot perfectly capture the complexity of ocean-atmosphere feedbacks. By contrast, forecasts for the 1997-98 El Niño and the 2015-16 El Niño were resounding successes. Both events were among the strongest on record, and models predicted their strength and timing months in advance, giving governments valuable time to prepare. These successes prove that forecasting works, even if occasional misfires remind us of the system's complexity. La Niña events often prove trickier than El Niños. They can emerge more suddenly, persist longer, and evolve in ways that models struggle to capture. The 2020 to 2023 La Niña, for example, lasted for 3 consecutive winters, something that had not occurred in decades. Forecast models consistently predicted it would fade, only to be surprised when the cold waters persisted. This prolonged La Niña influenced everything from Atlantic hurricanes to western drought, costing the US billions in damages and disrupting global agriculture. Scientists are still analyzing why models underestimated its persistence, and the answers may lie in poorly understood processes in the deep ocean or in interactions with other climate drivers like the Madden-Julian Oscillation or the Indian Ocean Dipole. These lessons are pushing forecasters to refine models and better incorporate flavors of ENSO events, whether the warming or cooling is centered in the eastern or central Pacific, which can drastically alter impacts. The rise of artificial intelligence and supercomputing offers a new horizon for prediction. Machine learning models are being trained on decades of ENSO data, learning to recognize subtle precursors in sea surface temperatures, wind anomalies, and subsurface heat content. Some AI systems have even shown skill in forecasting ENSO beyond the traditional 6 to 9 month window, potentially cracking the spring predictability barrier. Unlike traditional physics-based models, which simulate the Earth system step by step, AI can detect correlations and patterns that might otherwise go unnoticed. Still, AI forecasts require careful validation. A pattern recognized in historical data may not hold under future climate conditions. That is why scientists see AI as a complement to, not a replacement for, physics-based models. At the same time, supercomputers are becoming more powerful, enabling higher resolution models that simulate the Pacific Ocean and global atmosphere in greater detail. NOAA's recent upgrades allow simulations at scales that capture mesoscale eddies and fine-grained wind patterns, while ECMWF's new supercomputer in Bologna, Italy, promises unprecedented forecasting capability. Hurricane forecasting is another arena where these technologies are paying dividends. ENSO exerts a powerful influence on hurricane seasons. El Niño tends to suppress Atlantic hurricanes by increasing wind shear, while La Niña tends to fuel them by reducing shear and warming ocean waters. NOAA's high-resolution hurricane models running on supercomputers now incorporate ENSO conditions into seasonal outlooks, improving accuracy for how many storms might form and how intense they might become. AI-driven models are beginning to help as well, identifying atmospheric precursors of rapid intensification, a nightmare scenario where storms like Hurricane Ian explode in strength before landfall. By combining ENSO forecasts with hurricane models, scientists are getting closer to predicting not just the number of storms, but also their likely severity months in advance. For communities along the Gulf Coast and eastern seaboard, this information is invaluable, shaping evacuation planning, insurance pricing, and infrastructure readiness. What might the next decade look like for Americans as forecasting improves? The potential is transformative. Farmers in Iowa and Illinois could make planting decisions months earlier, choosing crop varieties suited to expected rainfall. Ranchers in Texas might adjust herd sizes before drought arrives, avoiding feed shortages. Utilities in the Northeast could stockpile natural gas if a La Niña winter is predicted, reducing the risk of price spikes. Insurance companies could more accurately set premiums, stabilizing markets that are currently destabilized by climate uncertainty. Even everyday families could benefit from better forecasts, whether through more accurate energy bills, more reliable food prices, or improved disaster preparedness. The economic ripple effects are enormous. Billions of dollars in avoided losses each year could result simply from better foresight. But forecasting alone is not enough. The next decade will test whether Americans can translate predictions into action. Knowing that a strong El Niño is likely will not protect California if its water systems are not resilient to floods. Anticipating a La Niña hurricane season will not save Gulf Coast homes unless evacuation plans and building codes are enforced. Forecasting must be paired with adaptation, investments in infrastructure, public health, and community preparedness. This is where science meets politics and economics, and where the success of ENSO prediction will ultimately be judged. What is clear is that prediction is improving, and the horizon is brighter than ever. NOAA, ECMWF, AI, and supercomputers are converging to provide humanity with unprecedented foresight. There will always be surprises. ENSO is too complex to tame completely, but the tools at our disposal are stronger than they've ever been. For Americans, this means the next decade could be one where ENSO's impacts are no longer sudden shocks, but anticipated challenges, met with preparation rather than panic. And that shift could redefine not just how we see the weather, but how we live with it. The effort to predict El Niño and La Niña has always been a battle against complexity, but it is also a story of steady progress. Each decade brings new tools and deeper understanding of how the Pacific Ocean and atmosphere interact. One breakthrough has been the ability to distinguish different flavors of ENSO events. Scientists now know that not every El Niño looks the same. Some warm the eastern Pacific, while others, known as Modoki El Niños, warm the central Pacific. These differences matter greatly, changing whether California faces floods, whether Asia endures drought, or whether Atlantic hurricanes are suppressed. Forecasting these subtle variations requires models capable of capturing small shifts in wind and ocean current behavior. Both NOAA and ECMWF have adapted their models to account for these complexities, and early evidence shows that accuracy is improving. For the public, this means that forecasts are not only about whether El Niño will occur, but also about what kind of El Niño it will be and what that means for everyday life. Looking ahead, the next frontier lies in coupling ENSO forecasts with decision-making systems that directly serve communities. Imagine school districts receiving ENSO-based health risk outlooks, preparing for severe flu seasons or heat waves before they arrive. Picture state governments adjusting water management policies in anticipation of El Niño rains or La Niña droughts. Envision farmers using mobile apps linked to NOAA forecasts to decide which crops to plant and when. These applications are within reach, but they require strong collaboration between scientists, policymakers, and the private sector. The forecasts exist. The challenge is to translate them into action quickly and effectively. Without that bridge, prediction remains academic, and lives and dollars are lost to hazards we saw coming. Of course, uncertainty will always be part of ENSO forecasting. No matter how powerful our supercomputers or how sophisticated our AI models become, the climate system retains elements of chaos. A burst of westerly winds in the Pacific or a sudden cooling pulse in the ocean can tip the scales in unexpected ways. Forecasts will always include probabilities rather than certainties, and society must learn to operate within that margin. The value lies not in eliminating uncertainty, but in narrowing it, giving people the best possible odds to prepare. In this sense, ENSO forecasting is much like medicine. It cannot promise perfect outcomes, but it can guide decisions that reduce risks and save lives. For Americans, the conclusion is clear. We may not be able to control El Niño or La Niña, but we are learning to anticipate them with increasing precision. Forecasting skill has grown from a few months to nearly a year in some cases, and AI may soon push that boundary even further. The ability to see these events coming means less surprise, less chaos, and more resilience. Whether it is farmers avoiding ruin, coastal residents surviving hurricanes, or families managing food and energy costs, the benefits ripple through every part of society. The next decade will be defined not only by how well scientists predict ENSO, but by how well communities use those predictions to adapt. That is the real promise of this science, turning knowledge into security. If you want to understand how global forces like El Niño and La Niña shape America's future, our weather, our economy, and our safety, subscribe to Crisis Lens. Here we break down the science, the forecasts, and the real-world impacts in clear, compelling ways. Because knowing what's coming is the first step to being ready.